In 2024, Elon Musk was promising 5 uncrewed Starships would launch to Mars in 2026, carrying Tesla's Optimus robots as a simulated crew to prepare for human landings by 2028. The plan was specific, ambitious, and seemed within reach after years of Starship test flights. But on February 8-9, 2026, Musk announced that SpaceX was shifting its near-term focus to building a self-growing city on the Moon, a goal he said could be achieved in less than 10 years, while delaying major Mars settlement efforts by about 5 to 7 years, and stating that SpaceX would still begin building a Mars city on a longer timeline rather than abandoning Mars entirely. What happened to the Mars mission that was supposed to launch this year? For over a decade, Musk has been making increasingly specific promises about getting to Mars. Unlike his earlier vague timelines filled with aspirational dates and rough estimates, the 2026 campaign had concrete details that seemed almost touchable. Exactly 5 Starships, specific robot cargo manifests, and a clear progression to human missions with defined milestones. SpaceX had billions in NASA contracts providing steady revenue streams, successful Starship test flights demonstrating key capabilities, and the engineering talent to make it happen. The company had evolved from a scrappy startup launching small payloads to the world's most prolific space launch provider. Yet when the moment came to execute the most ambitious Mars mission ever conceived, Musk didn't just delay Mars by a few months, he pushed it back by nearly a decade. This isn't just another story about missed deadlines or overly optimistic timelines. The 2026 Mars cancellation reveals the brutal technical realities that even the world's most advanced rocket company can't overcome, the geopolitical pressures reshaping space exploration in real time, and a fundamental shift in how we're approaching becoming a multi-planetary species. While SpaceX was promising Mars cities and million-person colonies, China quietly accelerated their own Mars sample return mission to 2028, potentially beating America back to the red planet entirely. The space race was being redefined, while America's most visible space company was recalibrating its most audacious goals. Musk's 2026 Mars campaign was remarkably specific compared to his earlier vague promises about reaching the red planet someday soon. 5 uncrewed Starships would launch in the 2026 Earth-Mars transfer window, a precisely calculated 26-month orbital alignment that occurs like clockwork. Each massive spacecraft would carry Tesla's Optimus humanoid robots as expendable crew members designed to operate autonomously in the harsh Martian environment. These robots would function as the advanced team for human exploration, scouting potential landing zones, testing life support systems, and building basic infrastructure before humans ever set foot on Martian soil. Musk said seeing Optimus walking on Mars would be an epic picture that would capture the world's imagination and prove that robotics and space exploration could work hand in hand. The mission architecture was breathtakingly ambitious in its scope and coordination requirements. If the 2026 mission succeeded in landing safely and establishing basic operations, SpaceX planned to scale up dramatically for the next transfer window. 20 additional Starships would launch in the 2028 window, mostly carrying more advanced robots, construction equipment, and cargo to build out Mars infrastructure at an unprecedented pace. The timeline progression seemed achievable based on SpaceX's track record of rapid iteration, uncrewed landings proving the technology in 2026, followed by first human crews in the 2028-2029 window, if the robotic advance team proved the landing sites were safe and operational. Internal SpaceX slides leaked to industry publications showed this wasn't just public relations theater designed to generate headlines. The company had developed detailed mission architectures spanning years of operations, logistics chains for moving equipment between Earth and Mars, and was actively planning the coordination of multiple simultaneous Mars missions. Engineers were working on everything from Mars-specific spacesuits to power generation systems that could operate in the planet's dusty environment. The scale was unprecedented in the history of space exploration. No space agency had ever attempted to land 5 large spacecraft on Mars in a single transfer window, let alone coordinate their operations with robotic crews operating millions of miles from Earth with communication delays measured in minutes. The logistics behind the 2026 campaign revealed the staggering complexity of Mars missions. Each Mars-bound Starship would require approximately 12 tanker launches to fully refuel in orbit, a delicate ballet of spacecraft rendezvous and propellant transfer. This meant the five-ship 2026 campaign would have needed over 50 successful Starship launches within a single launch window lasting just a few weeks. The orbital mechanics were unforgiving, missed the window, and the next opportunity wouldn't come for another 26 months. Each tanker would need to rendezvous precisely with a depot Starship floating in Earth orbit, transfer roughly 100 tons of cryogenic propellant through complex docking systems, then return to Earth for the next load in an endless cycle of launches and refueling operations. The vision extended far beyond the initial missions. Musk maintained his ultimate goal of a million-person Mars city by 2050, with the 2026 missions serving as the critical first step toward that seemingly impossible goal. The plan had momentum building across multiple fronts, funding from both NASA contracts and private investment, and public excitement that hadn't been seen since the Apollo era. SpaceX had become synonymous with making the impossible routine, from landing rockets on floating platforms to launching astronauts on reused spacecraft. What could possibly go wrong with their most ambitious plan yet? Orbital refueling emerged as the critical bottleneck that would ultimately doom the 2026 Mars timeline. The physics were unforgiving. Starship needs approximately 1,200 metric tons of propellant to reach Mars with meaningful cargo, but arrives in Earth orbit nearly empty after burning most of its fuel just escaping our planet's gravitational well. Without the ability to refuel in space, Mars missions were physically impossible. The spacecraft would be like a car trying to drive across the country with a gas tank that only gets you to the end of the driveway. SpaceX had successfully demonstrated small-scale propellant transfer between tanks within a single Starship during their March 2024 Flight 3 test, moving 5 to 10 metric tons of liquid oxygen while the vehicle coasted through space. NASA officials described the demonstration as successful by all accounts and a crucial step toward operational refueling capabilities. But this was just the first baby step in a marathon of technical challenges. The crucial ship-to-ship refueling demonstration, where two separate Starships would dock in orbit and transfer massive amounts of propellant, was originally planned for March 2025, but slipped to no earlier than 2026 as SpaceX struggled with the complexity of docking hardware, cryogenic fluid management, and dual-vehicle rendezvous systems operating in the vacuum of space. The technical challenges were immense and unforgiving. Liquid methane and oxygen must be kept at hundreds of degrees below zero to remain in liquid form. Any warming causes the propellants to boil off into space as useless gas, essentially evaporating the fuel needed for Mars missions. Managing these cryogenic fluids during the delicate process of docking two massive spacecraft, each the size of a skyscraper, then pumping hundreds of tons of fuel between them through flexible hoses, pushed engineering to its absolute limits. The margin for error was essentially zero. A single leak, failed valve, or docking mishap could result in explosive decompression or loss of mission-critical propellant. NASA's Donald Rapp, a respected Mars mission architect, calculated that each Mars-bound Starship would need approximately 12 tanker flights, with each tanker delivering roughly 100 tons of propellant to a depot spacecraft waiting in Earth orbit. This created a logistical nightmare requiring near-perfect reliability across dozens of complex operations. A single failed rendezvous could strand a Mars-bound Starship without enough fuel to complete its mission, turning a multi-billion-dollar spacecraft into orbital debris. The tanker flights would need to operate like a precision clockwork, with launches occurring every few days to maintain the schedule and prevent propellant boil-off from delaying the entire mission. Mars landing presented even greater technical hurdles that made orbital refueling look simple by comparison. Starship would be attempting to become the largest Mars lander ever by a factor of more than 100 tons when fully loaded with cargo and fuel for the return trip to Earth. This required mastering supersonic retropropulsion, the counterintuitive technique of firing rocket engines forward into oncoming supersonic airflow during descent to slow the spacecraft. The technique had been proven on Earth with Falcon 9 boosters landing back at Cape Canaveral, but Mars presented entirely different atmospheric conditions and challenges. Mars's atmosphere sits in an engineering nightmare zone, being only 1% as dense as Earth's atmosphere, but still thick enough to create intense heating during hypersonic entry at speeds exceeding 15,000 miles per hour. The atmosphere is too thin for traditional parachutes to slow such a massive spacecraft, but too thick to ignore during the fiery entry phase. The atmospheric density that makes Mars landing so technically difficult also makes it unpredictably variable, changing with seasons, dust storms, and daily weather patterns that could affect landing precision by miles. Without GPS satellites orbiting Mars to provide navigation signals, Starship would need to rely on advanced terrain relative navigation systems and autonomous guidance computers to identify its landing site and navigate precisely to predetermined coordinates. The spacecraft would need to recognize Martian landmarks in real time, compare them to preloaded maps, and adjust its trajectory while managing atmospheric uncertainties and avoiding surface hazards like boulders, craters, and slopes that could tip over the tall, narrow vehicle. The rocket plume from Starship's powerful Raptor engines would excavate massive craters in the Martian soil and blast debris at high speeds in all directions, potentially damaging the spacecraft or nearby equipment. This engineering challenge required pre-prepared landing pads, likely built by earlier robotic missions, adding another layer of complexity to an already staggeringly difficult technical challenge. Every aspect of Mars operations demanded technologies that existed only on paper, in computer simulations, or in limited Earth-based demonstrations that couldn't fully replicate the Martian environment. On February 8, 2026, in a series of posts that sent shockwaves through the space industry, Musk announced SpaceX was shifting focus to building a self-growing city on the Moon, achievable in less than 10 years, while acknowledging that a Mars city would realistically take 20-plus years to establish. The announcement came just months before the planned Mars launch window, representing a stunning 5 to 7 year delay to serious Mars settlement efforts and pushing realistic crewed Mars missions into the mid-2030s at the earliest, according to industry analysis. The decision was a masterclass in Musk's ability to reframe setbacks as strategic pivots. His reasoning was brutally practical and revealed a newfound engineering realism that surprised longtime Musk watchers. Mars launch windows occur every 26 months due to orbital mechanics, with 6-month transit times each way, while the Moon is reachable every 10 days with 2-day trips that allow for rapid course corrections and emergency returns to Earth. This fundamental difference makes lunar operations far better suited for the rapid iteration and debugging approach that had made SpaceX successful with Falcon 9 development. Every Mars mission mistake costs years to identify, understand, and fix. Every lunar mission mistake costs days and can be corrected on the next flight. The business realities driving the pivot were impossible to ignore. SpaceX's $4.2 billion in NASA Human Landing System contracts for the Artemis program created enormous financial pressure to focus Starship development on lunar missions for Artemis 3 and 4. These contracts provided guaranteed revenue streams and clear technical milestones, unlike Mars missions which remained largely unfunded beyond initial development work. NASA had already pushed the first Artemis lunar landing to no earlier than 2028 due to delays across multiple systems, including Starship's orbital refueling capabilities, creating a natural alignment between SpaceX's technical challenges and NASA's revised timeline. The Moon-first strategy offered a compelling technical argument that resonated with engineers even if it disappointed Mars enthusiasts. Lunar operations would allow SpaceX to mature all the critical technologies needed for Mars: orbital refueling, cryogenic propellant management, precision landing of heavy payloads, long-duration life support systems in a much lower-risk environment with abort options, and near real-time communications with Earth. If something went wrong on the Moon, astronauts could return to Earth in days rather than waiting years for the next Mars transfer window. NASA's official Moon-to-Mars architecture explicitly treats lunar operations as a proving ground for Mars systems, meaning SpaceX's pivot actually aligned their business interests with long-term Mars exploration goals rather than abandoning them. The Moon would serve as humanity's first off-world industrial base, a place to test technologies, train crews, and build the infrastructure needed for more ambitious deep space missions. Lunar resources, including water ice that could be split into rocket fuel, could eventually support Mars missions by providing a refueling depot beyond Earth's gravity well. Musk insisted that the mission of SpaceX remains the same, making humanity a multi-planetary species, but acknowledged that the Moon offered a faster, more achievable path to establishing a self-sustaining off-Earth civilization that could serve as a backup for humanity in case of global catastrophe. The pivot represented a rare moment of public humility from Musk, admitting that Mars was harder than anticipated while maintaining the ultimate vision that had driven SpaceX since its founding. While SpaceX delayed Mars missions by nearly a decade, other nations accelerated their own red planet ambitions, creating a geopolitical shift that caught American space policymakers off guard. China dramatically accelerated their Tianwen-3 Mars sample return mission to launch around 2028, with samples potentially returning to Earth by 2031 in what would be a stunning achievement for the Chinese space program. The mission represents a quantum leap in complexity for China, planning to collect at least 500 grams of Mars material using advanced drilling systems and possibly helicopter or robotic assistance, far more sophisticated than any previous sample return attempts by any nation. This aggressive timeline could allow China to return the first Mars surface samples to Earth before the United States, a scenario that seemed impossible just a few years ago when America dominated Mars exploration. The geopolitical implications became even more stark after NASA effectively canceled their Mars sample return program due to costs that had ballooned from initial estimates to an eye-watering $8 to $9.6 billion, with completion pushed to the late 2030s or 2040s. Congressional budget committees, faced with such massive cost overruns, drastically cut funding and effectively killed the program that was supposed to demonstrate American leadership in Mars exploration. Japan added another layer to international Mars competition with their MMX mission, launching in 2026 to sample Mars's moon Phobos and return at least 10 grams of material by 2031. While smaller in scope than China's surface mission, MMX would demonstrate round-trip navigation to the Mars system and advanced sample collection techniques that could inform future missions. The mission represents Japan's growing ambitions in deep space exploration and their willingness to tackle technically challenging missions that advance both scientific knowledge and national prestige. The competitive landscape revealed a fundamental shift in space exploration philosophy. While America's most visible private space company was promising transformational Mars cities and million-person colonies, other nations focused on achievable scientific milestones that would demonstrate technical capabilities and return valuable data to Earth. China and Japan were playing a different game entirely, one focused on incremental progress and proven results rather than revolutionary breakthroughs and inspirational timelines. NASA officials, when pressed about American Mars timelines, still describe a crewed Mars landing by 2040 as aggressive and audacious, requiring sustained political support, consistent funding, and successful lunar operations throughout the 2030s to build the necessary experience and infrastructure. Independent expert assessments from aerospace consultants and academic researchers consistently place the earliest credible human Mars landing in the late 2030s or 2040s, suggesting that SpaceX's revised timeline finally reflects engineering reality rather than aspirational marketing. Musk's Mars timeline revisions follow a remarkably consistent 15-year pattern that reveals how complex engineering projects evolve from initial optimism to practical reality. In 2011, during SpaceX's early years when Falcon 9 was still proving itself, he confidently predicted humans on Mars by 2021 to 2026. In 2016, riding high on successful Falcon 9 landings and growing NASA contracts, he promised crewed Mars missions by 2024 to 2025. By 2026, with Starships still struggling through test flights and orbital refueling unproven, he's pushed serious Mars settlement work to the 2030s. Each revision maintains the same ultimate vision, a million-person Mars city by 2050, while the near-term deadlines continuously slip by 5 to 10 years as technical realities emerge from engineering analysis and actual hardware testing. The pattern reflects a fundamental tension in how Musk operates as both an engineer and a public figure. The inspirational timelines serve crucial purposes. They attract talent, generate public excitement, secure funding, and push teams to attempt seemingly impossible goals. But they also create cycles of disappointment when reality inevitably falls short of the ambitious promises. The 2026 cancellation differs from previous delays because it came with a clear alternative strategy backed by billions in NASA funding to execute it, rather than simply moving dates around on a PowerPoint timeline. SpaceX President Gwynne Shotwell, known for her more conservative public statements, had offered a different internal perspective throughout 2024, suggesting humans on Mars were roughly a decade away, around 2034, much closer to the company's new official timeline, and revealing internal awareness that public timelines were overly aggressive. Shotwell's comments suggested that while Musk focused on inspirational messaging, the engineering teams were working with more realistic assessments of technical challenges and development timelines. The shift from Mars first to Moon first represents SpaceX maturing from a company that promised revolutionary breakthroughs on aggressive timelines to one that delivers incremental progress on proven revenue streams with clear technical milestones. Orbital refueling, still demonstrated only at small scale with limited propellant quantities, remains the keystone technology that must work reliably before any deep space missions become possible, and it remains unproven at the operational scale required for Mars missions. The abandoned 2026 Mars window may ultimately be remembered as the moment SpaceX transitioned from inspiration-driven timelines designed to capture public imagination to engineering-driven realities based on actual hardware performance and technical constraints. The company that once promised 5 Starships departing for Mars this year was now methodically working through the unglamorous technical challenges that make such missions physically possible rather than just conceptually exciting. SpaceX didn't abandon Mars in 2026. They finally got serious about the engineering realities that make Mars missions possible rather than just inspirational. The 5 Starship armada that was supposed to thunder away from Earth this year was always more aspiration than engineering reality, a vision that captured imaginations but couldn't overcome the fundamental technical challenges that still plague deep space exploration. Orbital refueling remains unproven at the massive scale required for Mars missions. Mars landing systems exist primarily in computer simulations rather than flight-tested hardware, and the logistics of coordinating multiple simultaneous Mars missions were staggering in their complexity and single points of failure. But the pivot to Moon first isn't a retreat from Mars ambitions, it's finally a realistic strategy for achieving them. By 2033, if SpaceX delivers on their lunar commitments and NASA's Artemis program succeeds, they'll have demonstrated orbital refueling at operational scale, precision landing of heavy payloads on airless worlds, and long-duration operations far from Earth with all the life support and reliability challenges that entails. Those same technologies, proven and debugged through lunar operations, make Mars missions not just possible but probable. The irony is profound. While SpaceX was promising immediate Mars cities, China's methodical approach to Mars sample return missions launching in 2028 may actually return the first Mars samples to Earth, while America continues debating timelines and funding. The race to Mars isn't over, it's being redefined by different players with fundamentally different strategies and definitions of success. China focuses on achievable scientific milestones that demonstrate technical capabilities. SpaceX builds the transportation infrastructure for eventual settlement and industrialization. Musk's vision of a million-person Mars city by 2050 might still happen, though it seems increasingly optimistic given the technical challenges that have emerged. But if it does happen, it won't be built by the company that promised 5 Starships launching to Mars in 2026. It'll be built by the company that chose to master the Moon first, learning hard lessons about life support, construction, and survival in hostile environments, then using that hard-won foundation to reach for the red planet with proven rather than theoretical technologies. Sometimes the fastest way to Mars is the long way around, building capabilities step by step rather than attempting revolutionary leaps. Sometimes the most ambitious dreams require the most patient execution, proving each technology and operational concept before betting everything on a single mission window. The 2026 Mars cancellation may have disappointed those hoping to see Optimus robots walking across Martian landscapes this year, but it may also represent the moment when Mars settlement shifted from science fiction inspiration to engineering reality.